Hi everyone, it's just a video of me going through a step 3 2020 question 4 actually, which is on matrices and vectors. Now I really like this one. I fancy that I could have got, I think I would have got 18 out of 20 actually in exam conditions. It was just the last little bit where I missed something obvious. Well, it's always obvious in hindsight, isn't it? But I definitely didn't notice it at the time, so perhaps it isn't obvious. But it's a nice question, I really do. I mean, I've always said I quite like matrices and vectors and planes and stuff. It's a fun topic. But yeah, I like this one, and I wanted to show you why I think it's a good question to possibly have a go at in the real thing if something like this comes up. Okay, so we're told that r dot n equals 0 as a plane, and n is a unit vector. Okay, before we even start, they want us to prove a couple of things, which actually I didn't end up using in the question, but which definitely can be used, I'm certain of that, to make some things slightly quicker. But I just want to show you what my thinking was in it. Okay, so P is a point with position vector x, which does not lie in the plane. Show that the point Q with position vector x minus, so let's just write it down. The point Q has position vector, so OQ is x minus x dot n. Now that's a scalar, isn't it? And then we're multiplying that scalar by the vector n. So that looks a bit weird, that setup. But this, we've got to prove this lies on L. Prove this lies on the plane P, you know, the plane pi or whatever. Okay, we're going to prove it lies on that. Okay, so let's do it. R dot n equals 0. Well, we're going to plug this in here as our r, aren't we? So we're going to have x minus x dot n. That's a scalar. We're multiplying that by n, and then we're going to dot that with n, yeah, and that equals 0. Okay, so what we're going to do first is we're going to apply the distributive property of the dot product, and so we're going to apply that through here, and we're going to get x dot n minus, now look at this, that's a scalar times a vector, so we're going to dot that n with that n, so we're going to have x dot n multiplied by n dot n. Oh, and I don't want to say equals 0 because I'm just going to investigate the left hand side. Yeah, in other words, what r dot n equals. In fact, let me write it as r dot n. So, and then hopefully turn it into 0. So r dot n equals this, which equals this. Okay, which equals, now the one thing we need to work out here is what is n dot n? What happens when you take a unit vector and dot it with itself? Well, pick a unit vector, I don't know, something like 1 over root 2, 1 over root 2. And watch what happens when you dot it with itself, 1 over root 2, 1 over root 2. You're going to get a half plus a half, which is 1. Yeah, now does that happen for all unit vectors? Yes, it does. Yeah, let's say the unit vector, let's give it a little hat to make it clear, is a, b, c. Yeah. Oh, and let's multiply it by 1 over root of a squared plus b squared plus c squared. That guarantees it's a unit vector. Yeah. Well then, n hat dotted with n hat equals that multiplied by itself. Yeah. Now remember that what we're going to have here is ABC dotted with ABC, and then we can times the scalar components together at the end. When you times that by itself, you're just going to have 1 over a squared plus b squared plus c squared, and so we've got a squared plus b squared plus c squared from the dot product there over a squared plus b squared plus c squared, and that equals 1. So whenever you dot a unit vector with itself, you get the answer of 1. Yeah, and you might do that working in a little box in the exam, just say consider, you know, yeah, and that at least shows the examiner that you know worked it out for yourself basically in the exam if you weren't aware of the result. I believe you could have just used the result without proof. Anyway, so we end up with x dot n minus x dot n, which obviously equals 0. So x minus x dot n multiplied by n lies on the plane. Now to argue that PQ is perpendicular to the plane, that's a little bit easier, because what is PQ? PQ is OQ minus OP. Yeah. Now OQ is simply this, and P is x. And so you've got x minus x dot n multiplied by n minus an x, that equals minus x dotted with n multiplied by n, yeah, and that is a scalar multiple of the normal vector of the plane. So you just say this is a scalar multiple, this is a scalar multiple of n, which is normal to the plane, which is perpendicular or normal, hence PQ is perp to the plane. There we go. A little bit of explanation. Okay, so let's get started with the main question now, because we've proved those two little quirky results. Okay, first, when I read through this first, I thought this sounds really good. I like this, because basically they're showing you that if you know where I, J and K end up after a transformation, then you know the matrix transformation. And that's one of the things I teach initially when I'm teaching matrices. So if you know where the vectors I and J end up after doing a reflection or a rotation, then you can immediately write down the matrix that represents that reflection or rotation or enlargement or whatever. Yeah, so that's what I'm going to do. Sorry, I'm just rubbing this out to give myself a little bit more space here, because I'd like to be next to the question so I can see it and talk about it. Okay, but yeah, I really like this question. It was no doubt that it was really nice. Okay, so let's do it. Let's just get rid of some of that, give ourselves a bit more space. I should have probably just dragged the whole sheet lower. Never mind. But that quirky little start, I didn't really think it was too bad. I think I've seen it before as well. I think it's come up before that, so make sure you can do it. Okay, so the thing is, that start can actually put you off from the rest of the question. The rest of the question is nice. So we're trying to show that the image of I is this after we've reflected it in this plane where a squared plus b squared plus c squared is 1. Well, if you reflect a point in a plane, my general strategy to reflect a point in a plane, and this normally applies with numbers, is I'd find, we've given 1, 0, 0 here, yeah, I'd first find the equation of this line, yeah, which is going to be r equals 1, 0, 0 plus lambda times, okay, the direction, well, the direction of this line is parallel to the normal vector of the plane, so it's going to be, have that equation there. That's definitely the equation of that line, and note that lambda equals 0 here, yeah. We can just find out where this hits the plane by plugging it into the plane. Well, we're going to get 1 plus lambda a times by a plus lambda b times by b plus lambda c times by c, and that should equal 0. So I'm just plugging this, the equation of this line, or if you like the parametric coordinates of this line, into this plane here. I'm just solving it, and I'm going to get a plus lambda times a squared plus b squared plus c squared, yeah, which we know is 1. And so you can see that lambda is minus a here. Okay, so that tells me that lambda is 0 there, and lambda is minus a there, and so the reflective point is going to have a lambda value of minus 2a, because lambda just counts you up and down the line, yeah? So that's my reflected point here. So what I'm going to do now is I'm just going to plug lambda is minus 2a into here and hope to get this, yeah? So what do I get? So r equals 1, 0, 0 plus minus 2a times by a, b, c. Now that gives me 1 minus 2a squared here, that doesn't look so good, but then minus a 2ab minus a 2ac, yeah? Whereas minus 2ab and minus 2ac look fine, this doesn't look so good until you remember that a squared plus b squared plus c squared is 1. And so if I plug that in there and take off a 2a squared from it, I get this, yeah? And so I can just say now that that equals b squared plus c squared minus a squared minus 2ab minus 2ac, yeah? Okay, so we've done that, and then it just says find the images of j and k under t. It doesn't say, you know, work out or, you know, prove that or show that. Now that means we can just use a symmetrical argument here, because obviously the way that worked for I, bearing in mind we've completely generalized this result, the way it works for j is just going to be like the equivalent, but, you know, using symmetric kind of arguments. And let me show you what I mean. So for j, we're just going to have 0, 1, 0 is going to go to, right, let's try and figure it out. Now, these, obviously it's the y component which is going to be affected by the, kind of Pythagoras relationship. And rather than taking away a squared, I'm going to be taking away b squared here. So I'm going to have a squared plus c squared minus b squared. All that's happened here, of course, is that your a's have become b's, and I'm talking about going from here to here. Your a's have become b's, your b's have become c's, and your c's have become a's, essentially. Although b and c are, basically you just got to, in fact, it's probably best not to look at it like that. Just look at it like, well, when I was dealing with 1, 0, 0, clearly a is the odd one out, and that's because it sits in the x component's position. And so all I'm going to have here, notice I've got the a's included on the other two coordinates, so I should have the b's included here. So I'm going to have minus 2ab minus 2bc, yeah? And that should take care of that. Now I've got the b's in both of these, and I'm taking away a b squared there. And then for k, it's going to be exactly the same thing, yeah? Don't go through all that working again, it just isn't worth it. And so I'm going to have here, now I need this one, I'll do this one first, a squared plus b squared minus c squared. So I've got that done, and then this is going to be minus 2ac minus 2bc. And now, of course, I can write down the matrix. The matrix representing the transformation M is going to be simply where I goes, so b squared plus c squared minus a squared. I might as well put down a squared plus c squared minus b squared in here, and a squared plus b squared minus c squared in there, and then I'll put the other ones in here, minus 2ab minus 2ac minus 2ab minus 2bc, and then minus 2ac minus 2bc. Cool. Okay, so our y's have b's, z's have c's at the end, x's have a's at the end, and yeah, it's all good. Okay, so that was the first bit. I quite like that. Part 2 was just basically applying this result because it represents a reflection in the plane. Yeah. Find the Cartesian equation of the plane, so that's nice. Okay. So all I did was I just thought, well, this is a reflection in the plane, and this is a reflection in the plane. I just used the result without thinking. So I used the diagonals actually. I said, okay, so b squared plus c squared minus a squared, that must be a 0.64. And then a squared plus c squared minus b squared, that must be a 0.36. And then finally a squared plus b squared minus c squared, that must be a 0. And I called them a, b and c, and I just added them together because I could see straight away you're going to knock out 2 letters, which is a bonus. So I had a plus b, well that's going to be giving me 2c squared is 1, giving me c is 1 over root 2, plus or minus, a plus c gives, now this time we're going to get rid of the c's and the a's, so we're going to get 2b squared is 0.64, half that you get 0.32, which is 32 over 100, 16 over 50, 8 over 25, square root it, you get plus or minus 2 root 2 over 5, and then b plus c, well we're going to have the c squareds cancel, the b squareds cancel, so obviously 2a squared is 0.36, that's 36 over 100, which is which is 18 over 50, which is, yeah, sorry, I've got to divide it by 2 first, that gives me 0.18, that's 18 over 100, which is 9 over 50, square root it, and you get 3 over 5 root 2, which is of course, plus or minus, 3 root 2 over 10, plus or minus, yeah? Now a quick little bit of inspection that these are negative, and remember those are minus 2bc and minus 2bc. That tells me that maybe b and c are both positive or b and c are both negative. But here, and this is minus 2ac, well that tells me that one of a or c must be negative, so I let a be the negative one, yeah, and you get the same answer either way. went for minus 3 root 2 over 10, and then B and C are both positive to make sure it produces that matrix. And I wrote this as root 2 over 2, and then when I got my, you've got to write down here the final Cartesian equation of the plane. So we just plug in these values, so you get minus 3 root 2 over 10x plus 3 root 2 over 5y plus root 2 over 2z equals 0. Cross out the root 2's, it's lovely that they'd vanish. Times everything by 10, you're going to get minus 3x plus 4y plus 5z equals 0, and you're good. Obviously, if we'd done A as positive, then B and C would have been negative, but you end up with exactly the same result. Okay, part 3. The matrix M represents a rotation through angle pi about the line through the origin, parallel to this vector, where a squared plus b squared plus c squared is 1. Find the matrix M. Okay, I got this. I was pleased to get this because this is when it started becoming difficult anyway. So far, basically up to that, I didn't really think I'd done too much difficult, but this is the hard of it. I was thinking, how do you reflect, how do you rotate something in a line in 3D space? I was puzzling over that, but then I realised, hang on, the angle is pi, so that's 180 degrees. I'm rotating 180 degrees in a line in 3D space. If you rotate that, by pi radians, 180 degrees, it's exactly the same as reflecting it in the line, and that's what made me much more comfortable with this step. It's like, oh, okay, rotating a line by 180 degrees, the same as reflecting in the line. So I used a very similar approach then to what I used in part 2. So I said, okay, let's consider just 1, 0, 0, because I'm happy working that out, and then I can just use symmetry for 0, 1, 0, and 0, 0, 1. But if you're trying to reflect that in a line, and we know our equation of the line is, say, lambda a, b, c, well, you need to make sure that you're finding a line perpendicular to that line, Now, how do we get from this point, let's call this point A, up to the line, let's say, the point on the line is B, Well, the general vector AB here is going to be OB, which is this, minus OA. So you're going to get lambda A minus 1, lambda B, lambda C, Well, we need to make sure that that vector is perpendicular to the direction of this line. So make sure AB is perp to R, I'll call this R1, and we're going to try and find the equation of the line R2. We're going to use like lambdas and mu's for this, can I point out that R2's direction, needs to be whatever we find the value of lambda for here. So let's make sure firstly that AB is perpendicular to R. So I'm just going to make sure that lambda A minus 1, lambda B, lambda C, if I want to make sure it's perpendicular, then when I dot it with the direction of this line, it should equal 0. That gives you lambda A squared plus B squared plus C squared. I'll omit some of the working there, that's dead easy to do. Minus A equals 0, but that equals 1, so lambda equals A, In other words, lambda must be equal to A for that to actually be at right angles, And so now I can write down the equation of R2. R2's equation, we need a point on the line, 1, 0, 0, and then we need the general direction of the line. Now I'm going to use mu for this. Now the general direction of the line needs to be this one, So I'm going to get A squared minus 1, and then AB, AC, Now note once again that mu equals 0 here, and mu is going to equal 1 when you're at the point of intersection, And you can see that because where do they intersect? Well, they intersect when lambda is A, and when lambda is A, you can see that this point is A squared plus B squared plus C squared. A squared, B squared, C squared. Cool. That's going to be the coordinate of that point, because when lambda is A, you get A squared, B squared, C squared, and so that's that point on that line. And so if we want this to be equal to A squared, B squared, C squared, well, we need mu to be equal to 1, because remember, lambda equals a. Oh, where's my coffee? Let me just pick up my coffee. Sorry, I'm a bit thirsty this morning. And what we've got for R2's equation, I should actually put on the lambdas here. There we go, lambda AB, lambda AC, lambda. Well, sure enough, when lambda equals, yeah, can I just rewrite this? Because I've got to write in the lambda there, sorry, plus mu times lambda A minus 1, lambda B, lambda C. Okay, right. Sure enough, oh yeah, and I've got this, I said lambda, yeah, look, this is wrong. Little mistakes creeping in. So lambda is A, that's going to give you A squared, AB, AC, that's better. And then sure enough, and I could have done it before because my thinking was right. Let me just take out the lambda because I don't need that. That's just the point at which it's perpendicular. So all I need here is A squared minus 1, AB, AC. And so sure enough, when mu is 1, you get exactly this point, and therefore when mu is 2, you're going to get the reflective position of the point, yeah? So mu equals 2 is going to be where I ends up after the transformation. So all I've got to do now is plug in mu is 2, and we're going to get 2a squared minus 1 plus 1, 2a squared minus 2 plus 1, which is 2a squared minus 1, and then 2ab, 2ac. Likewise, let's just put it like this, likewise for j, it's going to go to, right, let's use this symmetry argument again. Okay, so these are going to have like 2ab and then 2bc in here, and then the middle term is going to be 2b squared minus 1. And for 0, 0, 1, we're going to have 2ac, 2bc, and 2c squared minus 1. Yeah, I hope you can see where I'm getting those figures from. I'm just using a symmetrical kind of argument for what's going to happen with I, j, and k. It's just going to revolve around. Don't do the working again, it takes too long. Okay, so we can now write down n. We've got 2a squared minus 1, and then 2ab, 2ac, 2ab, 2b squared minus 1, 2bc, and then 2ac, 2bc, 2c squared minus 1. Okay, so we've done part 3. Identify the single transformation represented by a matrix NM. Now this is the mark I missed, and I can't believe I missed it. I think it's because I was working on several bits of random paper, trying to save paper. Now that didn't help because I couldn't see m written down next to it. Now m is b squared plus c squared minus a squared. And then it's got like minus 2ab, minus 2ac. I didn't see that these matrices were basically identical. And I started even looking to try and times them together. I mean, what a stupid idea that is. You have to laugh at yourself sometimes, don't you? This is a squared plus c squared minus b squared, isn't it? And this is going to be a squared plus b squared minus c squared. Okay, and that's minus 2bc. Now look at this. I just forgot that a squared plus b squared plus c squared is 1. So I can, of course, write this as basically the negative of the M matrix here. Disappointed I missed this. A squared minus b squared minus c squared. This is n as well, yeah? 2ab, 2ac. It's boring writing it down again, I know. Then, yeah, b squared minus a squared minus c squared. And c squared minus a squared minus b squared. And then 2bc, 2bc. Okay, so which that equals then minus m. Now this makes loads of sense because what we're saying therefore is that nm equals m and then m negative. Well, that's what nm equals. But of course M is self-inverse. Why is M self-inverse? Because it's a reflection. And if you reflect a point in a plane and then reflect it again in the same plane, you get back to where you started. So this should equal minus I, yeah, because anything which is self-inverse equals I. Now that is a reflection, scale, this is an enlargement, scale factor -1, center 0, 0. There we go, and we're finished, we're done. By the way, this is obviously what it should be as well, because think about what you've done. You've reflected a point in a plane, yeah, with a normal ABC, yeah, parallel to ABC. So you've reflected a point in this plane, yeah. So maybe that's gone from there up to here. Let's do it in different colour. So that's gone from there to there. Then you're reflecting it in a line, and that makes this go from here to here, yeah. Now what's going on here? Well, it's kind of like when you reflect in X then in Y in the 2D space, you end up with a rotation of 180 degrees. That's all that's going on here, you know, which is another way of looking at a scale factor enlargement, scale factor -1. So yeah, you know, it's kind of got a nice answer. This, it really has. It makes a lot of sense. Anyway, hope you enjoyed the video. I really like that question. It's one of my favourites so far. I've only worked through the first 4 questions on step. I do want to on 2020 step 3. I do want to show you this one next because I really enjoyed this one as well. Where I found I probably would have got 11 or 12 out of 20 rather than 18 out of 20. But there we go. Okay, hope that's useful. Keep up the hard work, everyone, and bye bye.